Right, ladies and gentlemen, my last two videos on this account were about deriving these two formulas, and I'm gonna do it again in a different method, because why not? Now, my chalk is almost dying out, but I am going to do a little bit of explanation of a different topic first, so we can, get to this part. We're going to talk a little bit about complex numbers. Now, when you, represent complex numbers in a plane like this, where you have the imaginary axis here, you have your real axis here, so that should actually be IM. And then you can plot a complex number, for example, 1 plus I, by having 1 on the real axis and 1 on the imaginary axis, and that's your complex number 1 plus I, right? So let's say we have two complex numbers. We have 2 plus I, which would be there. So let's get rid of u. Let's put 2 plus I, and let's put another one here, 3 plus I, right? What we can see is that each of these has an angle with respect to this horizontal over here, and so, like that. And what we can do is, with complex numbers, if we were to multiply these two, we would find another complex number, in this case 5 plus 5i, which is going to be, somewhere up here. And actually, what we would realize if we were to, plot this in the same way, is that this angle here, let's call this theta, in relation to this one. So if this is the 2 plus I, we'll call this angle alpha. If this is the 3 plus I, we'll call this angle beta. And actually, what we can realize is theta is equal to alpha plus beta, because when you multiply complex numbers, their angles add. Now, another thing to note about complex numbers is if we had a complex number z equals to a plus bi, it can also be represented as r multiplied by cos theta plus I sine theta. Now, all this really means is that there are two different ways of representing the same thing. So you can either use the length and the angle, or you can use the different components a and b. But that's two different ways you can represent a complex number. So let's for a second imagine we have two different complex numbers, one with a length of r1 and an angle of alpha, another with a length of r2 and an angle of beta. And let's say we try to multiply these. So, we'd have r1 cos alpha plus I sine alpha multiplied by r2. Oh, wait, no. We can put the bracket here. Not r squared, sorry, r2. And that's going to be cos beta plus I sine beta. My chalk is really on its last legs here, but we know what the result of this calculation will be is because, their lengths will multiply and their angles will add. So we'll end up with r1, r2 cos of alpha plus beta plus I sine alpha plus beta. And so now we can use this equation here to figure out values for cos of alpha plus beta and sine of alpha plus beta, which we are going to do now. So to make life easier for us, I've just removed the r1 and r2 from both sides, and so we're going to start multiplying out these brackets. So we're going to have cos alpha, we should put an equal sign there, cos alpha, cos beta, plus I sine beta cos alpha, plus I sine alpha cos beta, and then because we have plus I on both sides, they'll multiply to get minus 1, and so we'll have minus sine alpha sine beta. And now what we can do to make this match this form is take out a factor of I from the two terms that have it, and so we'll get that this is equal to cos alpha cos beta plus sine alpha, sorry, minus, that should be minus sine alpha sine beta plus I multiplied by sine beta cos alpha and plus sine alpha cos beta. This chalk really is finished. But as you can see, if we then match this up, we get that sine of alpha plus beta is sine beta cos alpha plus sine alpha cos beta, which is what we have up here. And we get the cos of alpha plus beta is cos alpha cos beta minus sine alpha sine beta, which is what we have up here. And that, ladies and gentlemen, is a third successful way of deriving these angle formulas.